In this video, we're going to start looking at the topic of statics in equilibrium. To begin with, I want to define two different words. The first word is equilibrium and the second word is static. Let's start off with equilibrium. If a body is in equilibrium, the resultant force in any direction will be zero. So if we use Newton's second law, F is equal to ma, and we resolve vertically, the resultant will be zero. If we resolve horizontally, the resultant will be zero. There is no acceleration. So that's equilibrium. If we now look at the word static, a body is said to be static if there's no movement. Now there is a difference between the two. So with equilibrium, we can have now an object, and let's take it a particle. We can have a particle that is moving, but it's still in equilibrium. So if we had a particle that had a constant speed of 16 meters per second, there's no acceleration. So whilst it's still moving, it's in equilibrium. When we're talking about static equilibrium, which is what this section is about, it's when we have an object, which we'll model as a particle, that is stationary in one place and is not going to move. An example might be a book on a table. Unless we apply a big enough external force, the book will remain in static equilibrium. It will only accelerate now if we can apply a big enough force. So what we're going to do is work through a range of different problems and use Newton's second law, resolving vertically and horizontally, and we're going to look when the resultant is zero. So we'll come across forces such as the normal reaction force, the weight, tension, thrust and friction. So let's just have a look at this in a real life situation. Where does this pop up? Let's take now a boat in a harbour. Let's just go ahead and model this up. So let's do a really simplistic model. I might have a boat and it might have a rope with a given tension there, might have another one and another one. What we could say now are these forces are going to be balanced if now we're in equilibrium. T1, tension 1, we could have now T2 and we could have T3. If there's no resultant force of the boat, then these forces are said to be in equilibrium. We could use a triangle of forces if we wanted, or we could just go ahead using Newton's second law, F is equal to ma, and we could now say if in equilibrium, resolving now in the vertical direction is zero, resolving in the horizontal direction is zero, if in equilibrium. So with now adequate information there, we could just go ahead and find the values of now the tensions. We'd need sufficient information, but we could go ahead and do that. So let's look at a basic example of this. Let's just draw a little particle. So what we'll do is have a particle. I'm going to apply 3 different forces. It won't always be 3 different forces. We might get more. But this just gives us a nice, and in fact we'll put that one just there. Let's go for that one just there. Then I'll have now another force, and let's put one at an angle. Let's put it just here. And then let's put one now horizontal. So what I'm going to do is just go ahead and I'm going to have a horizontal here, and this is going to be an angle, inclined an angle. Let's go for, let's just put 30 degrees. So let's have a known force. So let's say this is going to be 12 newtons. I'm going to have 2 different forces, and let's call this one P, let's call this one Q. So what we might be asked is now to find the values of P and Q such that this particle is in equilibrium. So what we have then is a force P, inclined at an angle of 30 degrees. We've got Q, which is going to be at right angles, so we're acting now directly down, and we want to go ahead and do this. What we're going to do is use Newton's second law, F is equal to ma. We can say if in equilibrium, so if in equilibrium, resolving now vertically is going to be equal to 0, resolving horizontally is going to be equal to 0. We can see that I'm going to start off by resolving horizontally. If I resolve vertically, I've got 2 unknowns. So what I want to do now is resolve horizontally to find the value of P. Then I'll sub it into now the vertical, resolve vertically, and then go ahead and find Q. So let's now look at resolving, and what we'll do, we'll resolve now, and this is going to be resolving horizontally. That's going to be equal to 0. We've got F is equal to ma, which is now Newton's second law. So let's go ahead and do that. So if I now resolve, and I'm going to resolve horizontally, let's consider the horizontal component of this force. The horizontal component of this force is going to be P cos 30. We're looking now for this force acting in the horizontal plane. If you want to see this as a little right angle triangle, the magnitude of the hypotenuse is P. We've got an angle of 30. this is the hypotenuse, this is the adjacent. So we can say that P cos 30 minus the force acting in the opposite direction, which is minus 12, must be equal to 0. You could put P cos 30 is equal to 12 as those forces are balanced. I prefer to write it as Newton's second law, F is equal to ma, and then just go from there. So P is going to be 12 over the cosine of 30 degrees. If you know the cosine of 30 degrees, the cosine of 30 degrees is root 3 over 2. So we could write this as an exact value, and what's that going to give me? P is 24 over root 3, so we could rationalise that now as 8 root 3 newtons. Of course, straight for a calculator if you want, check that you're in degrees mode, and then it would be now 12 over the cosine of 30 degrees. You're not expected to know all of these angles necessarily for any given course. That gives us 8 root 3, or 13.9. So 13.9 newtons, and that is given to 3 significant figures. So that now is the value of P. All I've done is resolved horizontally. Let's now look at resolving vertically to find Q, given that we've got P. So if we resolve now, F is equal to ma, we've got now Newton's second law. So I'm now going to resolve vertically. If we consider the vertical component of this force, again using a little right angle triangle, this is the adjacent, this is the hypotenuse, this is the opposite. This has a magnitude of P, so we can say that this is going to be P sine of 30 degrees minus Q, which is acting directly down, must be equal to 0. So let's go ahead and write this. We've got now Q is going to be equal to P. Well, P is 8 root 3. We've just found that out, just here. And then we got the sine of 30. The sine of 30, if you know that, is 1/2. If not, straight for a calculator. So we have 4 root 3 newtons, which is going to be half of this one right here. And we will just go ahead. Let's just divide this answer by 2. And that's going to give us now 6.93. So 6.93 newtons, and that is correct to 3 significant figures. So 3 SF. So all we've done is resolve now to find one unknown and essentially use simultaneous equations to find the other unknown. Based on the fact that when we use Newton's second law, F is equal to ma, we resolve horizontally and vertically, the resultant in any direction will be 0. There's no acceleration. That is static, it's not going to move. So in this unit, we're going to look at problems such as these. We're going to look at problems just on a horizontal plane. We're going to look at inclined planes and just go through a range of different problems. All I want to do in this one is get the idea of using Newton's second law, F is equal to ma, and setting to 0 to solve. So let's go ahead and do a slightly more challenging one. And then in later videos, we will look at examples of inclined planes and so on and so forth. So this time we've got a 5 kilogram bob is suspended in air in equilibrium attached by 2 unequal inextensible strings as shown. The 2 strings are then attached to the ceiling. We need to calculate the tension in each string. What I like to do here is draw a quick sketch. We've got our particle here, and the number one error in these types of questions is not to put the weight on, or just simply leave it out. The weight is the force acting down. Weight is mass times by gravity, as we've seen in the past. W is equal to mg newtons. So we've got now the weight of the bob, which is 5g newtons. G is 9.8. What we now have are 2 of these strings. So what we're going to have is the following. So we're going to have 1, and all I'm going to use is now an alternate angle. If this is 30, then it's 32 the horizontal. I prefer working in this way, but you certainly don't have to. So all I'm doing is putting the information on. We've got now a 30-degree angle. We've got a 45-degree angle. I'm going to call this one now T1. So we could call this T1, we could call it P and this one Q, or we could have T1 and T2. T generally stands for tension. So what we can state at this stage, if in equilibrium, we can say now F is equal to ma, we will have now F is equal to 0. So resolving upwards, this is going to give us 0. Resolving now across or horizontally, that's going to give us 0. What we've got here now are 2 unknowns, and we need to go ahead and find them. We need to calculate the tension in each string. So if I resolve now horizontally, I can get an expression for T1 in terms of T2. If I now resolve vertically, I'm going to still have an equation involving t1 and t2. So what we're going to end up with is simultaneous equations. So if I go ahead and resolve now horizontally, let's consider the horizontal component of this force right here. That is going to be t2 cos 30. I'm now going to subtract away the horizontal component of this force right here, and that will be t1 cos 45, and that is going to be equal to 0. Using Newton's second law, if we resolve parallel now to that line, we get 0. Now at this stage I could use exact values, you don't have to, but we could right now, the cosine of 30 degrees is root 3 over 2, and we could set that equal now to t1, and then we'd have the cosine of 45 degrees, which is root 2 over 2. So if I wanted at this stage, I could say that t1 is going to be equal to root 3 over root 2 t2, or anything along those lines. I don't have to, I could come back to that, but that's what I could do if I wanted. So what we could say then is t1, just rationalising this, would give us now root 6 over 2 t2. I'm going to leave that alone and just call this equation 1. Let's now consider resolving vertically. So if I resolve vertically now, I'm going to think about the vertical components of these forces. So if I think about this now, I'm going to have t1, and then it will be the sine of 45 degrees. All we're looking for now is the vertical component. This is the hypotenuse, which is t1. This is the adjacent, this is the opposite. I want to know how much the force is contributing here. So what we have then is that plus now t2, and remember this now is this is giving us all the forces in the vertical direction acting upwards. t2 sine of 30, and that now subtracting away 5g will be equal to 0, as now that is the force acting in the opposite direction. So what we have here is t1, and then we have root 2 over 2, and then we've got now t2. Now the sine of 30 is going to be equal to 1/2. Again, you can get that on a calculator, and that's equal to the mass times by gravity, which is 5g. What I can do now is sub this in. So if I wanted, I can solve at this stage for t2 and then plug it back in. So I've got now root 6 over 2 t2, and I'm going to multiply that by root 2 over 2, and then I'm going to add to that now t2 multiplied by 1/2, and that's going to be equal now to 5g. Okay, if I now multiply both sides by, what are we going to have? Let's just tidy this up. That's going to give me root 12 over 4. Again, with this third work, use a calculator if you like. So with root 12, we've got 2 root 3 over 4. And I'll just simplify this as I go. t2 plus now 1/2 t2. And I'm just writing this in, and that's going to be equal to 5g. So all I'm looking to do here is solve for t2. And as stated, you can do that on a calculator. What I've got here now is root 12, which is 2 root 3 over 4. So if I multiply both sides now by the 2, we're going to have root 3 t2 plus now t2, and that's going to be equal to 10g. So we've got now t2 root 3 plus 1 is equal to 10g. So we could write now that t2 is going to be 10g over root 3 plus 1 newtons, and that is what we call an exact value. If we wanted to work out a numeric value, we could do. Let's go ahead and do that. So what we have then now is 10g, but it's 10 times 9.8, so I'll put it as 10 times 9.8, and then we've got now root 3, and we're going to add to that 1. So this now, I'll round this to 3 significant figures, 35.9. So T2 is going to be 35.9 newtons, and that is to 3 significant figures. So throughout my calculations, I was working with exact values and SIRS. Use a calculator, as this isn't part of it. These are just some of the calculations that you'll come across. Now if we look at this, we can get T1 from that. So T1 is going to be equal to now root 6 over 2, and then we're going to have the 35 ... and so on and so forth. So let's go ahead and do that. All I'm going to do now is multiply this. So multiply this, and you might want to store this just in case you make an error. we'll multiply this now by the root 6 over 2, and that will give us T1. So we end up now with 43.9. So T1 is going to be equal to 43.9 newtons, and that is given to three significant figures. So there we go. That is using a slightly more challenging example with simultaneous equations, but we're still relying on the fact that this is now a particle that's in equilibrium. It's not moving, it's suspended in the air. It's not going to, so imagine this is some kind of sign hung up, or some banner. That is not going to be jumping around. It's not going to be accelerating horizontally or vertically, and we just go ahead and apply these particular formulae using Newton's second law to solve. So there we go, brief introduction now to statics in equilibrium. In the next few videos we're going to work through a whole range of problems, but that is the basic idea behind it.